In this session, I will focus on laundry detergents, which belong to a large family of chemicals called surfactants. You may ask, how is this related to crude oil? It is a fair question. Many key detergent ingredients are produced from petroleum fractions. A common example is linear alkyl benzene sulfonate, or LAS, often abbreviated. It is produced from normal paraffins and benzene, both of which come directly or indirectly from crude oil processing. Surfactants are natural or synthetic chemicals that promote the dispersion of one phase into another, especially the dispersion of oils into water. Their primary function is to reduce the surface tension of water and create a bridge between a nonpolar substance and water. Milk is a natural example. It is an emulsion of fat droplets in water. The fat does not dissolve in water, but milk proteins act as natural emulsifiers, stabilizing tiny fat droplets in the aqueous phase. Surfactants are also known as detergents, wetting agents, emulsifiers, foaming agents, and dispersants. Let us begin by outlining what you will learn in this part. To keep the session engaging, I will begin with a brief history of surfactants and detergents. Then, I will explain the cleaning mechanism in simple language. Although we will discuss laundry detergents, the same ideas apply to many products that are emulsions, such as hand creams, shampoos, liquid detergents, and even industrial formulations. For an industrial example, consider pesticides and herbicides. Many are oils or low-solubility organic liquids that must be dispersed in water for application. Later, you will see how the main detergent precursor, linear alkyl benzene, LAB, is produced. LAB itself is not a surfactant. To give its surfactant properties, it must be sulfonated. An SO3 group is added to the benzene ring to form an acid. Neutralizing that acid with caustic soda produces a salt with excellent cleaning performance. Finally, I will review two industrial routes for producing laundry detergent powders, low density and high density. The primary reference for this video is Ullmann's Encyclopedia of Industrial Chemistry. Archaeological evidence suggests that ancient Egyptians used soda ash, obtained from wood ash, as an early detergent. They also observed that adding sodium silicate softened hard water and improved cleaning performance. Around 2500 BC, one of the earliest recorded soaps is attributed to the Sumerians, who lived in Mesopotamia, in the region of modern-day Iraq. For thousands of years, soaps were widely used for cleaning hair and skin. Over time, soap was also adopted for laundering fabrics. In the early 20th century, more effective laundry soaps were developed by adding supporting ingredients. For example, sodium silicate and sodium carbonate improved performance, especially in hard water. In 1928, Birch and co-workers converted natural fats to alkyl sulfates, which was an important step toward modern synthetic detergents. Alkyl sulfate salts have strong emulsification power. You may know the brand Tide. It was introduced in the United States in 1946 as a household laundry detergent. Today, detergents are essential in daily life and contain many ingredients. In this session, we will focus on the key concepts and the main industrial building blocks. To do that, we first need to understand the cleaning mechanism. Let us examine the structure of soap and compare it with sulfonate-type detergents. Soap is commonly produced by neutralizing a fatty acid, such as stearic acid, with sodium hydroxide to form a sodium salt. At the molecular level, soap has two distinct parts, a hydrocarbon tail and an ionic head. The hydrocarbon tail is hydrophobic and has affinity for nonpolar materials, such as oils. The ionic head is hydrophilic and dissolves readily in water. Now, imagine a droplet of oil in water. Without surfactants, oil and water remain immiscible and the oil collects on the water's surface. If we add soap, the soap molecules migrate to the oil-water interface. Their hydrophobic tails embed in the oil droplet, while their hydrophilic heads remain in the surrounding water. This stabilizes the droplet and prevents droplets from merging. With mechanical mixing, large oil droplets break into smaller ones, and soap molecules stabilize those smaller droplets. The result is an emulsion, a stable dispersion of oil droplets in water. During washing, the oil phase can represent grease and soil on the fabric. Dispersing that oily phase into water allows the dirt to detach from the fabric and be carried away. A key limitation of soap is its performance in hard water. Calcium ions can replace sodium ions, forming calcium soaps that are insoluble and precipitate. This consumes soap molecules, reducing cleaning performance. A practical solution is to add agents that bind calcium ions or to use surfactants whose calcium salts remain soluble. A major class of such surfactants is alkyl benzene sulfonates. The molecular structure of alkyl benzene sulfonate is similar in concept to soap. It has a hydrophobic hydrocarbon tail and a hydrophilic head that includes a benzene ring and a sulfonate group. This structure, again, creates a bridge between water and nonpolar oils, enabling the formation of stable dispersions. The same emulsification mechanism described for soap applies here. Modern detergents, however, are not just surfactants. They contain additional ingredients that enhance performance and allow the product to work under challenging conditions, such as hard water. Let us look at the major components of detergents. The primary active ingredient in a detergent is the surfactant, which enables the dispersion of nonpolar oil into water. Examples include alkyl polyethers, alkyl sulfonates, and quaternary ammonium compounds. Detergents also contain builders, which support cleaning performance by binding or removing alkaline earth ions in hard water, helping remove soil and stains, improving handling and flowability of powder products, supporting safety and environmental goals, and reducing manufacturing cost. Examples include zeolites as ion exchange materials and EDTA as a chelating agent. Phosphates were highly effective builders, but their use has been restricted in many regions due to environmental impacts such as eutrophication. Oxidizing agents, such as peroxyborates or hypochlorite, can be added for whitening and stain removal. Auxiliary additives are used for specific conditions. For example, enzymes such as proteases help remove protein-based stains. Foam regulators control foaming in machine washing. Corrosion inhibitors protect machine washing components. Optical brighteners may appear as small colored particles in powder detergents and improve perceived whiteness. With that overview, we can now connect detergents to crude oil by examining how linear alkyl benzene is produced. The production of linear alkyl benzene, or LAB, begins with normal paraffins. These can be separated from petroleum fractions or produced from light olefins through controlled oligomerization. In the first major step, normal paraffins are dehydrogenated to normal olefins over a platinum catalyst. Although hydrogen is produced by the reaction, hydrogen is also mixed with the feed to reduce catalyst deactivation and suppress side reactions, such as cracking and coke formation. The feed is preheated using heat exchange with hot process streams and then heated further in a furnace to reach the reaction temperature. Because the reaction is endothermic, the reactor outlet is cooler than the inlet, which is another reason external heating is required. Hydrogen is separated from the reactor effluent in a gas-liquid separator. A portion is recycled to the inlet, and any excess hydrogen can be sent to other refinery units. To increase overall conversion, the hydrocarbon stream can be processed in a second reactor, often operated at a lower temperature. Next, fractionation separates hydrogen and light hydrocarbons formed by mild cracking. The olefin-rich stream then reacts with benzene in an alkylation reactor, commonly using hydrogen fluoride as a catalyst. Excess benzene is used to drive the reaction toward alkyl benzene formation. Downstream, fractionation columns recover benzene and recycle unreacted paraffins. Finally, the LAB product is separated from heavier alkyl benzenes. The LAB stream is then sent to sulfidation, where the sulfonate group is introduced to create the detergent active ingredient. A typical sulfonation unit that converts linear alkyl benzene to linear alkyl benzene sulfonic acid, LABSA, uses a continuous falling film thin film sulfonation reactor. Dry SO3 gas, often diluted with dry air or an inert carrier, contacts a very thin, downward-flowing film of LAB on the inner walls of cooled tubes. Because sulfonation is highly exothermic, rapid heat removal is essential. Jacket or shell-side cooling water removes heat quickly, stabilizes the film, and minimizes side reactions, such as dark color formation and over-sulfonation. LAB and SO3 enter at the top. LAB forms a uniform liquid film inside the tubes and flows downward, while SO3 flows concurrently and reacts at the gas-liquid interface. The reacted film exits as crude LABSA, typically containing small amounts of byproducts, such as saltones, and traces of unreacted LAB. This stream then enters a digester or aging vessel, where controlled mixing and temperature allow reaction completion and improved byproduct conversion. Overall residence times are short, commonly under 10 minutes. Downstream, a cyclone or similar separator removes entrained liquid from the gas stream. The off-gas is then treated in an appropriate scrubber to remove residual SO3 before venting or further handling. The LABSA product is collected and commonly sent to neutralization, often after dilution with chilled water, using caustic soda, NaOH, to produce linear alkyl benzene sulfonate, LAS, which is subsequently blended with other ingredients to formulate detergents. Key design themes include dry feeds, a uniform thin film, strong and reliable heat removal, short and controlled contact time, and effective off-gas scrubbing. This slide summarizes a common route for producing low-density, spray-dried laundry detergent powder, which is typically porous and fluffy. Liquid ingredients, such as the sodium sulfonate LAS solution and sodium silicate, are fed continuously to a mixing tank. Solid ingredients are added using controlled feeders. The exact formulation depends on each manufacturer's recipe. The resulting slurry is pumped to the top of a large spray dryer and atomized through nozzles into fine droplets. A spray dryer is a continuous unit that converts a liquid feed, solution, slurry, or emulsion into a dry powder by 1. Atomizing the liquid into very fine droplets to create a large surface area, and 2. Contacting those droplets with a hot gas inside a drying chamber so water evaporates rapidly and solid particles form before the outlet. The main components are the feed pump, atomizer, pressure nozzle or rotating disc, hot gas generation system, heater and fan or blower, the drying chamber, and a powder collection system, cyclone and or bag filter. Product moisture and particle size are mainly controlled by inlet and outlet gas temperatures, gas flow rate, feed rate, and droplet size set by atomization conditions. Spray drying is widely used in detergents because it is fast, continuous, and can produce powders with controlled particle structure, though it can be energy intensive and may face wall deposition and dust handling challenges. In this process, superheated steam enters near the bottom and flows countercurrently upward. Steam rapidly evaporates water from the droplets. Because drying occurs in seconds, a shell forms quickly and a porous particle develops, helping create the characteristic low-density powder. Using steam can improve heat transfer and reduce ignition risk compared with hot air. In addition, exhaust steam can sometimes be recovered and reused elsewhere in the plant, improving overall energy efficiency. The dried particles are discharged and transported by pneumatic conveying, which helps cool the solids and limit excessive particle breakage. A cyclone then separates the powder from the conveying and exhaust gas by centrifugal force. Dusty gas enters tangentially, a vortex forms, particles move to the wall and fall to the hopper, and the cleaned gas exits through the top. Key factors include inlet velocity, cyclone size, pressure drop, and powder properties. Very fine or sticky powders may require multi-cyclones or a downstream filter. Next, the powder passes over a vibrating screen to remove oversized material, while fines are commonly recycled to the front end. Finally, heat-sensitive additives such as enzymes and fragrances are blended in after drying, and the product is sent to packaging. Spray drying is energy intensive, but it produces the familiar low-density detergent powder many consumers prefer.
For large-scale industrial users, high-density detergent powder is often preferred to reduce packaging and transportation costs. The next slide introduces that route.
High-density detergent powder is typically produced using a different route than spray drying. Solid ingredients such as zeolites, sodium carbonate, fillers, and recycled off-spec powder are fed to a mixer while liquid ingredients, e.g. sodium silicate and additional surfactants, are added simultaneously. Unlike the spray drying route, the mixer outlet is a damp, paste-like material, not a free-flowing slurry. This higher solids, lower air entrainment feed is one reason the final product can achieve higher bulk density. A common drying step is a steam-heated drum dryer, which is an indirect contact dryer. The detergent paste is spread as a thin film on the outside surface of a rotating metal drum. Steam enters the drum through a rotary joint, heat transfers through the drum wall, and evaporates water from the film. A doctor blade continuously scrapes the dried layer from the drum as a dense sheet or flakes, which are then milled or granulated to the target particle size. If the steam is superheated, it first cools to its saturation temperature and then condenses on the inner drum wall. The latent heat of condensation provides most of the heating duty, so effective condensate removal via a siphon and steam trap is critical. If condensate accumulates, it creates a thermal resistance, lowering heat transfer, drying capacity, and product consistency. This route supports high-density powder production because the material forms as a compact sheet or flake with fewer internal voids than many spray-dried particles. Density can be increased further through granulation and compaction downstream. Key control variables include film thickness, drum speed, residence time, steam pressure, temperature, condensate removal performance, and scraper alignment. The outlet vapor and entrained fines are typically handled with a cyclone, and recovered solids are recycled. In some designs, part of the steam vapor stream is recovered for heat integration, and excess steam can be used elsewhere in the facility as a heating medium. After drying, a vibrating screen ensures a controlled particle size distribution. Fines may again be recycled to stabilize product quality. Finally, heat-sensitive additives, e.g. enzymes, bleaching agents, and chelants, are blended near the end, followed by fragrance addition in a final mixer. The finished high-density powder is then sent to bulk packaging. This overview is intentionally brief. The purpose is to illustrate how refinery-derived chemicals can be converted into familiar household products that may not seem connected to crude oil at first glance. In this session, you learned how a major detergent precursor, linear alkyl benzene, or LAB, is produced and then converted through sulfonation and neutralization into detergent active sodium sulfonate. You also saw at a high level how these active ingredients are combined with builders and additives to produce both low-density and high-density laundry detergent powders. Thank you very much for watching this session. I hope it helped you build a clear picture of the key concepts and how laundry detergent is produced from petrochemical products. Please continue with the next session on the paint industry.